Okay, so thank you all for coming to the first Quantum Fluids and Isolation seminar. So this isn't really an official Boston College seminar, but it's just something I thought up as a nice way to get basically the quantum fluids community together and share some interesting physics in this time of isolation. So just a few things before we give on our inaugural lecture is that, as I said before, just please have your cameras and your microphone off. I'm going to do it the same thing. Professor Lucas, you can keep yours on, of course. And if you do have questions during the talk, please raise your hand and then I'll unmute your mic. And I do encourage you to wait till the end, please, unless it's something very, very pressing. Okay. And this talk will be on YouTube later. And if you want to get future emails about QFI, just follow the Google group. Okay. So today we have our first speaker, QFI. We have Professor Andrew Lucas, who is quite well known in this community. He got his Bachelor's of Science at Stanford in 2012. He got his PhD at Harvard under Subir Sachdev, where he studied transport and hydrodynamics and holographic materials, strange metals, and graphene. He then postdoced at Harvard before postdocing at Stanford from 2016 to 2019. And then he, now he's a professor, an assistant professor at University of Colorado, Boulder in 2019. So please help me welcoming either by muting your mic and clapping or clapping electronically, Professor Lucas.
All right. So thanks for the introduction and the invitation. So today I'll give a bit of a kind of overview talk of some of the work that's been going on and which I've been involved in trying to understand, let's say, viscous hydrodynamics in electron fluids. Let me begin by just acknowledging all of my collaborators that I've worked with, at least on the projects in this talk. So there's groups of Andrea Young and Anya Jayek at UCSB, my PhD advisor, Subir Sachdev, along with Philip Kim at Harvard, and then a graduate student, Caleb Cook from Stanford. Okay, so maybe I can begin by getting, by sort of introducing the broader problem that we were motivated to understand when we first started thinking about hydrodynamic flows in electron fluids. So the bigger picture that we had in mind is a new framework or a new way of thinking about strongly correlated electrons and their transport and dynamical properties in solids. So, if we think microscopically, right, a solid is a very complicated system. It's Hamiltonian, its many-body Hamiltonian is very complicated. So in black here we have, let's say, electron, phonon, and impurity degrees of freedom. Let's imagine that these black terms for the electrons and phonons just have sort of quadratic kinetic energy. We can have some impurities, again, quadratic terms for the electrons. And then in red, there's a whole zoo of interactions. Here I've just written electron-electron and electron-phonon interactions. Typically, the way that we approach this problem in solid-state physics is to imagine that these red terms can be treated as perturbatively small. In practice, that's not true in general. Microscopically, generally, the electron and phonon terms are quite large. Now, in ordinary metals, whenever Landau's Fermi liquid theory applies, we can kind of get away. These interacting terms become irrelevant. At low temperatures, it's okay to treat them as small. However, there are a number of electronic systems where, for one reason or another, Landau's Fermi liquid theory doesn't apply, and these red terms are no longer small, and we really need some kind of new perspective to understand their transport properties. And since transport is quite easy to measure in experiment, this isn't entirely a theoretical exercise. Okay, so if we can't use perturbative field theory type approaches, at least a priori, it may seem quite limiting. Due to, well, a number of features of quantum mechanics, this is basically an intractable problem to put on a computer. So if you give me a generic model of a strongly interacting electron system, I can't just have my laptop spit out for you what the resistivity of that material would be. And there are a number of reasons for this. Firstly, just sort of an obvious statement, the Hilbert space of this many-body problem is exponentially large. Now, obviously, that's going to preclude any sort of exact diagonalization type solution, but you could ask, are there good approximate methods that we could use? For example, there are quantum Monte Carlo methods where you can try to replace a sort of exact quantum solution with an approximate solution based on statistical sampling. And for a generic Hamiltonian of this form, that's impossible because of something called the fermion sign problem. Now, there's many authors who have tried to get around this fermion sign problem by designing sort of special Hamiltonians to be sign problem free. And after all of that work, even after you have your sign problem free model that you can simulate, while you can extract thermodynamic properties of that system relatively easily, you can't extract transport properties very effectively. There's a very well-known numerical ill-posedness of going from the imaginary time data that the Monte Carlo spits out and trying to analytically continue that into real-time data. And unless you had sort of an exact numerical computation of all Matsubar frequencies, it just doesn't work very well. And just to emphasize, this is not a theoretical problem that has no relevance to a real system. There are many, many examples of materials that really do have these strongly correlated electron liquids, if you will, that aren't accessible using conventional methods. Just to give you one example, because this is the picture that I use in many talks, this is a sort of snapshot of a phase diagram of this complicated material. The x-axis here is X, the chemical doping parameter in this formula, and the y-axis here is temperature. The color shading on this plot basically denotes the power of resistivity, or the power of temperature that arises in the resistivity. So rho scales as temperature to some power. Everywhere where you see this orange here, labeled non-Fermi liquid, this corresponds to a resistivity that's approximately linear in temperature. And for many reasons, we're pretty confident that this system is not an ordinary Fermi liquid. And to understand the physics in this part of the phase diagram, we really need some kind of different approach to thinking about correlated dynamics. Okay, now it may seem a bit surprising that this is a hard problem in the first place. After all, while indeed an exact solution is kind of out of the picture, there's other problems that we've solved in the past that involve very strongly interacting systems with many, many degrees of freedom. And these are the dynamics of sort of classical liquids and gases. So for example, we design airplanes and we know how air flows around the wings of the airplane. Were we to solve for the dynamics of the air microscopically, it would involve a completely intractable computation with 10 to the 28, et cetera, degrees of freedom. It's completely hopeless. But we solve these problems quite efficiently by not talking about the dynamics of every single molecule in the air. Instead, we have an effective theory called hydrodynamics, which reduces this enormously difficult problem into a differential equation involving a few simple hydrodynamic degrees of freedom. So you might ask, why not take that same approach and try to apply it to a solid state system? Okay. And we'll talk in the next few minutes about sort of when you can and can't do that. But first, let's just get on the same page about what we might hope to achieve from this framework. So hydrodynamics is an effective description. When we use it to model air, we aren't able to understand all possible dynamical processes that take place in a gas by appealing to hydrodynamics. Okay. Only the processes that occur on sufficiently long time scales or if you will, frequency omega inverse time, multiplying some microscopic collision time, that product should be very small compared to 1, implying there are many collisions that take place on the time scales that we're looking at. And equivalently, we would like to look at very short or very long length scales compared to a microscopic mean free path. Once these two conditions are satisfied, it's plausible to expect that a sort of generic hydrodynamic description of your system can emerge. When these inequalities aren't satisfied, then you really need a sort of full microscopic description. We don't expect necessarily any universal dynamics to take place. Okay, so the basic idea of hydrodynamics is the following. We have a complicated microscopic system. It's chaotic. And on long time scales, essentially chaos has set in, and there's no possible way that we can keep track of the microscopic dynamics. The only thing that we might possibly hope to achieve is to keep track of where the electrons are. So let's imagine we have just an ordinary metal. We have electrons, bouncing around. There's impurities, there's phonons, other electrons, as we've discussed. And the only slow degree of freedom that we might expect is essentially the number density of the electrons at any given point in the metal. And the reason for this is that because electronic charge isn't being spontaneously created or destroyed, we know that an electron moving from one region to another has to sort of do so in a continuous path. Okay? And so if we see a rate of change of the number of electrons in any region, it must be because some electrons flowed outside of that region. And this is a local conservation equation, of course, and this will form the basis of our hydrodynamic description. Okay? Now, this equation is exact. It doesn't rely on our hydrodynamic assumptions in any way. Where hydrodynamics comes in is that we approximate that this current can be expressed as a simple function of the density itself, okay? So in general, right, this continuity equation is underdetermined. We have a density n, a charge current j. If these are unrelated, this is a true equation. It's a constraint, but it doesn't tell us very much. However, if we have this sort of a relation, like at least the average current that flows is related to the gradient of the average density, then we're in business. We can plug these two equations into one another and we get a closed equation of motion for the density. Now, why have I restricted myself to this simple form j equals grad n with these ... terms left over? The reason for this is that, as we've just stated, hydrodynamics is valid on long length scales. And that means in particular that the perturbative parameter that we're going to use to control our expansion is a wave number multiplying a mean free path. The wave number comes from the gradient. And so this is a first order term in our expansion. Okay? So we combine these two equations together and we get the ordinary diffusion equation. The last piece of the story, in addition to what I've said, is that this diffusion constant is not an arbitrary function of the density. It should always be positive. And this is sort of the most unsatisfactory part of this story from an effective field theory perspective. It's really still a subject of discussion over the past few years. But historically, what we said was just that if we look at this diffusion equation, it's unstable if the diffusion constant is negative. So stability and a second law of thermodynamics demand that this diffusion constant be positive. Okay. We've already mentioned that the diffusion constant should be proportional to a mean free path because this coefficient was first order in our gradient expansion. And this is kind of an executive summary of the simplest hydrodynamic theory. And it's a theory that's actually relevant in solids. This describes charge flow in a conventional metal. Okay. Maybe there's one more ingredient that we could add in an ordinary metal if we wanted to be really careful, which is that we could also include the energy density in addition to the charge density. Energy is also a conserved quantity in our universe. If we ignore Coulomb interactions, which I will do for the whole talk, that's sort of a sensible thing to do if we're not interested in time-dependent phenomena. If we go ahead and drop long-range Coulomb interactions, this is the hydrodynamic theory that describes most solids. Okay. So we just have two coupled diffusion equations for our conserved quantities. You can also think of this as a kind of local statement of Ohm's law. Now, at this point, we have to address, why does this hydrodynamics look very different from the hydrodynamics that we think of when we talk about liquids and gases, in the ordinary world that we see? The reason is that the ordinary classical liquid and gas have an extra conservation law, which our electron fluid is missing. And in an ordinary liquid and gas, in addition to essentially mass and energy conservation, we also have momentum conservation. Okay? So any collisions between air molecules or water molecules conserve the momentum of the molecules involved in the collision. And adding this conservation law completely changes the behavior of hydrodynamics. Okay? Now, in a typical solid, we don't have this extra conservation law because there are a number of processes that can relax momentum. For example, if we have impurities in our system, impurities basically by definition break translation symmetry. And by Nether's theorem, we know that this relaxes momentum. A more serious issue is that many crystals, especially those with large Fermi surfaces, have significant umklapp scattering. An umklapp process comes from the fact that the microscopic lattice also breaks translation symmetry from a continuous group to a discrete subgroup. You can translate by one lattice site, but not half a lattice site. Umklapp processes basically tell you that momentum is only conserved up to a crystal momentum, but that crystal momentum doesn't get to play a role in hydrodynamics. Okay, so if you can easily sort of exchange crystal momenta, you don't have an additional continuous conserved quantity. There's no hydrodynamic variable. Okay, so partly as just kind of a question of curiosity, we might ask, is it possible that for whatever reason, maybe umklapp and disorder aren't that important in at least one material, and so at least in this one context, perhaps we could see electrons behave more like a classical liquid than like these diffusion equations. More practically, there are a number of possible applications that you could find for an electron liquid, one of them being the basis of a high conductance nanoscale device. I'll comment a little bit on that as we go. So for various reasons, it would be interesting if we could find a quantum fluid of electrons that actually behaves more like a classical liquid than like this ohmic theory. In an ordinary metal, we definitely have the ordinary ohmic description. The reason for this is that, for example, we might have a lot of impurities. We have a mobile electron here in blue, and all it sees as it moves through this metal, crudely speaking, is a sort of zoo of impurities and momentum relaxing dirt. It bounces around, from one impurity to the next, and just like a pinball in a pinball machine, there's no momentum conservation. It just moves sort of randomly and diffusively. Okay, one possibility, and this was really the possibility that inspired us back in 2015, was that maybe one can think about some of these non-Fermi liquid regimes in experiment. I'm certainly not going to claim any one in particular, but maybe some of them could be thought of as kind of dirty metals. There's lots of impurities and momentum relaxing processes, but because they're very strongly interacting, rather than thinking of the electrons as these kind of little objects that kind of freely fly by each other unless they hit head on, we might think of the electron soup as this kind of thick liquid with very strongly interacting objects that are constantly interacting. And maybe the interactions are so frequent that even though there's all these impurities, there's still some kind of viscous behavior, at least on some intermediate time scales. Another possibility for how one might try to look for hydrodynamics, and this is a bit easier experimentally, is to give up on the non-Fermi liquid and to say, well, let's stick with an ordinary metal with a Fermi liquid. We know that the Fermi liquid at low temperatures doesn't have particularly strong interactions. And the lower we go in temperature, the weaker those interactions become. However, if we grew a very clean crystal, it could be the case that at some finite temperature, even though there aren't that many electrons and their interactions aren't that strong, there's even fewer impurities. And so the most likely thing for one electron to collide with is another electron. And then all we need to get rid of is our electron umklapp processes. If we can do that, maybe we can see our ordinary hydrodynamics with momentum conservation kick back in. Okay. So much of the experimental progress has really followed this last line of thinking. And this is mostly because it's simpler to compare experiments with theory. Okay. So the first thing that I want to talk about is how we can look for signatures of a viscous, clean Fermi liquid in an experimental system. Okay. All right. So the first thing that we should do is we should understand what hydrodynamics we're actually looking for. So we don't want to just see ordinary diffusion equations. We want something more complicated than that. And so we're going to imagine that in addition to charge conservation, we also have momentum conservation. The charge continuity equation, charge conservation equation that we'll write down will look a little similar to before, except that rather than having a diffusive term d grad n for the charge current, we'll say that the charge current can be thought of as a fluid velocity. If you have an isotropic Fermi liquid, this is a very sensible thing to do. In an isotropic Fermi liquid, this charge current is pretty much the same thing as the momentum density up to a factor of mass. Okay? And so this fluid velocity, we should actually think of as a proxy for the momentum density. Okay? So the effective mass, m, times density times velocity, we can think of this as the momentum density of our system. And then together with charge density, the densities of our two conserved quantities form the hydrodynamic degrees of freedom in the system. Now, if there were no impurities at all, the right-hand side of this equation would be 0. And so the remaining two terms on the left-hand side, this grad p here means pressure, and eta grad squared velocity, these two terms correspond to the divergence of the momentum flux tensor, also called the stress tensor. And just like this top equation, we could think of the second sort of linearized Navier-Stokes equation as simply a statement of momentum conservation. Okay. So each component of momentum would be conserved. Now, in a real metal, we always have some dirt, and so we can just think of fudging the right-hand side of this equation to put a minus gamma times v here. This gamma is a phenomenological parameter that we can actually compute quite carefully, at least in weakly disordered systems, although I won't say too much about it. Okay. Now, similarly to what we discussed before about diffusion, this coefficient eta is basically related to the mean free path between momentum conserving collisions, and this gamma ends up essentially being 1 over the momentum relaxing scattering length. Okay. Now we're going to ignore conservation of energy, and the reason for this, there's a few reasons, but the sort of dirty argument for this is just that if we think about a metal with a Fermi surface, all the mobile electrons sit at the Fermi surface. They all carry the same energy. So roughly speaking, the energy is just a chemical potential or a Fermi energy multiplying the density of electrons. And we've already accounted for density being a conserved quantity. Okay. So we want to just study these two equations. We have charge conservation, we have momentum conservation. And the most obvious feature of these equations is that they contain a length scale. And this is a consequence of the fact that momentum wasn't exactly conserved. So if we look at the ratio of eta over gamma and we take a square root, this object has the dimensions of length. If we look on large length scales compared to this, this square root eta over gamma, then we will just go back to ohmic transport, okay? One way you can think about it is that the fluid velocity will become fixed by the pressure gradient. The pressure gradient is proportional to the density gradient, and you can combine these two equations to recover Ohm's law. If we look on short length scales, however, then the right-hand side of this Navier-Stokes equation can be approximated as 0, and then we really have a viscous fluid, okay? So the question is basically, well, first, there's an experimental question of can you find a metal where this length scale is reasonable? And then secondly, and what I'll focus on more in this talk, how do you actually tell that you've found a viscous fluid if you had one? Okay, so one of the key shortcomings in quantum solid state physics relative to, let's say, ordinary liquids and gases is that in an ordinary liquid, there's all kinds of different experiments that we can do. We can, push fluids through pipes. We can measure flow rates. We can create vortices and so on. And we can measure all of these things because, they're at human scale. However, in these solid state devices, right, they're very small, and typically we're probing them electronically. And so how do you actually tell whether you have hydrodynamics if you have a solid state device? The original proposal for how to do this is very old. It comes from a Soviet physicist named Gurzhy in 1963. And what he proposed was basically to cut, let's say, a narrow channel of your solid. This channel will have width W, and he proposed that you should apply an electric field and drive a current or a fluid velocity through this channel. And all that we have to measure is the resistance per unit length of this channel. That's his proposal. Now, the way we can think about this resistance per unit length is that some of the resistance is coming from essentially just a kind of parallel resistors factor. The wider this channel is, the more places there are for current to flow, and so the resistance will go down accordingly. Okay? The more interesting factor we can think of as essentially the momentum relaxation rate. Because the current and the momentum are approximately the same thing, to degrade away our current, which is what we need to have happen to measure resistivity, we need to have momentum relax. So by estimating the momentum relaxation time in this channel, we can estimate the resistance per unit length that we measure in an experiment. If we have an ordinary metal where bulk impurities or momentum relaxing processes dominate this momentum relaxation, then we would expect that the resistance per unit length of this device is proportional to our 1 over W times a constant. Okay? And this constant will just be set by the impurity scattering time and won't depend on the geometry. Now, if we ignore impurities, but we assume that we have a viscous fluid, then if the width of the channel is large compared to our collision mean free path, there'll be lots of electronic collisions inside the device. And so we expect to form a hydrodynamic fluid inside of this channel. Now, these electron collisions we're taking to be momentum conserving, otherwise there's not much to talk about. So we've got a bunch of momentum conserving collisions. They're forming a viscous fluid in the middle of this channel, and the only place for momentum to relax is at the boundaries. Now, the decay time that we're interested in is then going to be set by essentially the decay rate of the hydrodynamic modes that exist inside this channel. These modes decay diffusively, but it's the diffusion constant for momentum, not for charge. The diffusion constant for momentum is set by the momentum conserving mean free path times the Fermi velocity of the device. And then because the time scale for diffusive modes to decay is 1 over the width squared, in this case, the width sets our length scale, we predict that the resistance per unit length of this device should scale as 1 over W squared times 1 over W, which is 1 over W cubed, with an additional temperature squared 1 over T squared prefactor, coming from the fact that the Fermi liquid mean free path scales as 1/temperature squared. Okay, so that's a very striking prediction. It both has a very unusual width dependence in resistance, as well as a very unusual temperature dependence, where the resistance drops as we increase temperature in a very good conductor. Okay, and that's quite unusual. Okay, lastly, if the channel is very small, then we just have a basically single particle picture going on. The momentum relaxation time is set by the transit time to get from one side of the channel to the other, and that transit time will be 1/W. So we expect to see 1/W squared scaling. Okay, so those are three different predictions, and in principle, they can be tested in experiments because experiments can very easily measure the electrical resistance of a device. However, there's a real issue of material quality. So most materials are not good enough, they're not clean enough to see this physics. The first compelling experimental hint of this effect came in the 90s in gallium arsenide. I don't think people really paid much attention to it at the time, but more recently, experiments in graphene have come around, and maybe they're a little more controllable, and these have become much more studied. Let me not focus on flow in a narrow channel, because for various reasons, mostly related to boundary conditions, that's actually not an ideal geometry to study. A somewhat better choice is to think of flow through a narrow constriction. So imagine, take the channel and just squish it, and then study how electrons basically flow through this narrow constriction between two much wider channels on either side. This exhibits many of the same features of flow through narrow channels that Gurji predicted. In particular, in the viscous regime, the resistance through this constriction should scale as 1/temperature squared. And an experiment was done in 2017 to look for this decrease in temperature of the resistance of this device, and this effect was seen. Okay, so this plot on the right-hand side shows you, as a function of temperature, a non-monotonic temperature dependence coming at three different charge densities in a device. And you can see that below around 150 Kelvin, we see this kind of Gurji predicted temperature decrease. Now, one reason that we're confident that this is the effect we think it is that if you look at these straight lines, they're actually predictions for what the flow in the ballistic limit would be. Okay, so at very low temperatures, we are very close to the ballistic prediction for resistance. Then to have this kind of super ballistic transport flow where the resistance is below the ballistic limit, that's a sort of clear signature of these viscous effects. Okay. Now, more recently, we've tried to understand these kinds of problems even better. So in addition to just understanding the total resistance of this device, we can also ask how the current actually moves through the device, because it turns out that actually that as well is very sensitive to whether you're in a viscous regime or not. Okay, so in this plot, what you're seeing is in the top panel, we have a sort of a color map of how much current is flowing through the device. Where you see black, that's no current, and so you can see a little constriction etched out here. And then yellow is high current. Then in the bottom panel, we're just looking at the current through the middle of the constriction as a function of width x. In panel 1, this is the prediction of ohmic flow. So if we have impurity limited flow, what you see is that the current bunches up at the edges of the device. This is essentially a lightning rod effect. If we're in a ballistic regime, then the current will mostly flow uniformly through the center of the device. There's a bit of a curl at the edge, just coming essentially from the thickness of the constriction. And then in the viscous limit, you can see that the current peaks at the middle of the constriction. Okay. And so in particular, 1 is very distinguishable from 2 and 3. So if we can image the current flow, we can really clearly discriminate where we are in the phase diagram of electron-electron versus electron impurity scattering. Okay. All right. So to image the current flow, we can use what are called nitrogen vacancy centers. This is basically a single quantum spin in graphene, and it's a very sensitive magnetic field detector. As the current flows through the two-dimensional graphene layer, it will create magnetic fields by the Biot-Savart law. And because we're imaging the magnetic field out of plane, we can actually uniquely map out the current flow from a single component of the magnetic field that we measure. So we hover this, this device about 150 nanometers above our sample, and this sets our spatial resolution to be about 150 nanometers. So you can think of this NV center as kind of like a camera. We scan it, 1 pixel at a time over the device, and we read out what the current flow is. Okay, so to calibrate the device, you can do an experiment at room temperature. At room temperature, it was widely believed that graphene was host to essentially significant momentum relaxing phonon scattering. And we can indeed see ohmic impurity or phonon limited transport. So just from this experimental image, you can already see that the current bunches up quite strongly near the edges of the constriction. If you try to now compare this with a theoretical model, this is actually the theoretical prediction. The current actually is very, very tightly wrapped around the edges of the constriction. But that 150 nanometer smearing that we mentioned actually sort of muddles this picture quite a lot. Okay. Nevertheless, you can see that there's 2 very clear peaks, confirming that we are in a sort of local diffusive regime. Okay. So now we can look both as a function of density and as a function of temperature, what happens to the current profile in this device. At room temperature, this device is always ohmic, okay? So CNP here means charge neutral point. This is sort of special. It's a non-Fermi liquid regime, which I won't say much about, at least for now. And then at these 2 finite densities, one an electron Fermi liquid, one a whole Fermi liquid, we again see 2 peaks, although not quite as deep. Okay. As you cool the system down, you see that the charge neutrality point still has these 2 ohmic peaks, whereas both the Fermi liquid regimes now have a sort of single peak in the middle of the constriction. Okay. We can then ask, we have a model for how much, or for how the current should flow through this device as a function of momentum conserving and momentum relaxing scattering lengths. And so we can ask essentially if we assume a given value of LEE and LMR and then pick the optimal geometry, modeling a function of, let's say, offset of the constriction with what we think it is, how big the constriction is in practice, and so on, we can come up with kind of an error map of where we could possibly be in a phase diagram. And these top 2 plots confirm for us that we are definitely ohmic. Okay, there's a very short electron momentum relaxing mean free path. And the mean free path that pops out of the simulations is essentially what we measure independently through a bulk transport measurement. So this image is quantitatively consistent with what we would have predicted. Okay, and we don't care very much what the electron-electron scattering length is because regardless of what it was, this device just is very big compared to the momentum relaxing length scale. Now, as we cool the system down, we can definitely rule out ohmic flow. And the computer thinks that the optimal flow is viscous. And the electron-electron mean free path that we predict is actually compatible with theoretical predictions. It's within 20 or 30% of theoretical predictions. However, due to the uncertainty in the geometry, we can't sort of definitively rule out ballistic flow. So there's this kind of big swath of parameter space that we can't really rule out. I think looking forward, it would be nice to do better and to rule out more of this phase diagram. But I think for these isotropic Fermi liquids, this is actually not so easy, at least with this kind of measurement. Okay, so nevertheless, I think that this experiment, it's quite nice that we can really image the breakdown of ohmic flow, and we think that we are imaging viscous flow. We can't sort of definitively say that, but I think it's quite promising. A complementary imaging experiment was done on a slightly different setup. So if you have a narrow channel, so now it's back to our old geometry, but you apply a magnetic field, a sort of similar effect is predicted. If you look at the electric field that's generated, like the Hall field that's generated when you push current through the device, it's predicted that that Hall current or Hall field is basically uniform in a ballistic regime and is parabolic in a hydrodynamic regime. And so in this experiment, you can see at 7.5 Kelvin, the field profile sort of looks much flatter at the middle of the device than it does at 75 Kelvin. And this is evidence for a ballistic to viscous crossover at lower temperatures, which is compatible with our sort of ohmic to viscous crossover imaged at higher temperatures. Okay, so that's all I want to say about isotropic Fermi liquids. Now let me move on to discuss a little bit about anisotropic Fermi liquids. So, most materials that we have in nature are not simple isotropic materials. Many of them are quite anisotropic. One example is palladium cobaltate, which has an approximately two-dimensional Fermi surface. I say it's approximately two-dimensional because in the third dimension, while this is very much a 3D material, the Fermi surface is quite flat, and so the quasi-particles don't really move very much in that direction. Experimentally, you can confirm that really you do have a big hexagonal Fermi surface with these rounded corners. Now, this material is of course one of a whole zoo, but I bring it up because there was an experiment done in 2015 where it was postulated that hydrodynamic effects were being observed, or at least the onset of hydro was being observed. So what they were imaging was essentially the resistance per unit length of a channel multiplied by width, so thus kind of an effective resistivity. And if you were in a ballistic regime, you would expect to see 1 over W, just as a linear plot on this curve. If you were in a hydrodynamic in a viscous regime, you would expect to see something more like 1 over W squared. As a function of 1 over W, these experimentalists grew a number of channels in this material. They measured this effective resistivity, and they found that the data sort of seems to be very weakly concave up. Okay. So this blue line demonstrates what you would predict if you didn't have any momentum conserving scattering, if you only had momentum relaxing scattering. And the red line includes some additional momentum conserving scattering. It's like a factor of 5 or 10 faster. And so they argued that this data is compatible with at least the onset of the Gurgey effect. Now, there's a number of puzzles about this, and we'll come back to at least some of them in a bit. One of them is the temperature dependence is not shown on this plot, and I will show you that a little later. The other one is that this material has a large Fermi surface, and in principle, umklapp effects could be significant. I don't actually really know why umklapp effects don't seem to be important here, but anyway. Okay, so the model that they used to compare this data with was a model of hydrodynamics with a circular Fermi surface, and a model, to be more precise, of the ballistic to hydrodynamic crossover using a circular Fermi surface. However, this model has a hexagonal Fermi surface, so you could ask, is that really appropriate, or do you see a very different kind of hydrodynamics and a different crossover from ballistic physics in a hydrodynamic regime? Okay. So we can set up a toy kinetic theory for a Fermi liquid with this anisotropic Fermi surface, and we can evaluate what happens in the hydrodynamic limit. What we find is the following. So as before, we'll have a charge conservation equation and a momentum conservation equation. Let me just take impurities out of the problem for simplicity. There are two changes to these equations relative to what you would expect for an isotropic Fermi liquid. The first one of them is that there's what Sean Hartnell would call an incoherent diffusion term, highlighted in red. This is coming from the fact that an approximate Galilean invariance of isotropic Fermi liquids has been broken. The hexagon is not rotationally invariant. Without Galilean invariance, the charge current and the momentum density can be different, even at leading order and low temperature, and that leads to this additional charge transport mechanism. In the viscosity tensor, we also see a new kind of term. So in our toy model, we have shear viscosity. This is sort of usual in fluid dynamics. Because this is a Fermi liquid, we don't have a bulk viscosity term at leading order and temperature. However, we do have one new contribution, which we'll call rotational viscosity. It comes with this kind of unusual tensor structure with two Levi-Civita tensors. And this really is a consequence of the hexagonal Fermi surface. You can't see it with an isotropic Fermi liquid. And this is, it's really not, Hall viscosity, it's a dissipative coefficient. It represents something sort of interesting. So what's going on here is the following. This hexagonal Fermi liquid, or Fermi liquid with a hexagonal Fermi surface, is arising from the fact that the microscopic Fermi surface is coming from a crystal lattice which explicitly broke rotational invariance. And the crystal lattice is approximately frozen for the electronic dynamics. And what that means is that if you try to sort of rotate this fluid, if you try to essentially rotate the Fermi surface in this crystal background, that's very energetically unfavorable, and it will try to relax back. It will try to rotate back. This essentially tells you that the stress tensor does not need to be symmetric because angular momentum is not conserved. And now you're allowed to write down the structure in the stress tensor that corresponds to rotational viscosity. In an ordinary solid, this effect can't happen because rotational invariance is broken spontaneously. Okay. Now, okay, we have this different fluid dynamics. Does this change the nature of the crossover from ballistic physics into viscous physics? So if we try to do an experiment looking for the Gurgey effect, do we have to see the same thing as we would in an isotropic Fermi liquid? So let's imagine that we have a Fermi surface, which is this hexagon. Because the hexagon breaks rotational invariance, we now need to be very careful about how the Fermi surface is oriented relative to the walls of the channel. Okay? As a function of the relative angle between the Fermi surface and the channel, we can see very, very different width dependences in the conductance of this channel, which is basically 1 over the resistance per unit length of this channel as a function of the width. Okay. At large widths, because we don't have momentum relaxation, we're seeing the conductance scaling as W cubed or G over W squared scaling linearly. This is the usual Gurgey effect, that's viscous flow. At small widths, we see G scaling like W squared, that's ballistic physics. But the value of G is very sensitive to the angle made with the Fermi surface. And as a consequence, you can get this very dramatic non-monotonic width dependence in your conductance. To understand where this is coming from, you can just imagine that we have a hexagonal Fermi surface sitting in the middle of our channel. all of the quasi-particles have to move normal to the Fermi surface. Now, if this Fermi surface is offset relative to the channel, then all of the quasi-particles can just bounce off of the walls of the channel. They all will sort of tend towards the walls and hit the walls. However, if the hexagon is aligned with the channel, then the particles at the top and at the bottom of the channel can just travel. They don't hit anything. They don't hit the walls of the channel. And until the quasi-particle hits the wall, its momentum isn't lost. So when you apply an electric field, if you have this ideal hexagon, you just accelerate the electrons at the top and bottom of the channel infinitely, and so get an infinite conductance. In the hydrodynamic limit, it turns out that the prefactor of this W cubed gives you essentially both the shear and the rotational viscosity together. And it's actually not trivial to think about how these might be distinguished. All right. Maybe the last point that I'll make given time is we can ask, is this model relevant for palladium cobaltate? And it turns out that the answer is no, somewhat unfortunately. And the reason why is sort of simple. After we did all this work, we came up with this model. And what you find is that if you plot the full experimental data set, both the temperature dependence and the width dependence of the conductance, and you plot it in our way, what you see is the following. So the more purple the curve, the narrower the channel, and the more red, the wider the channel. As you narrow the channel, the conductance goes up at low temperatures, and then it's sort of saturating around here. Now, if this were sort of ideal, then when you're deeply in the ballistic regime, all of these devices would have the same conductance when divided by W squared. Okay. And we see that these curves aren't completely aligned, and I'll come back to that in a moment. Okay. All right. So there's definitely no Gaussian effect in terms of the temperature increase in this conductance as a function of temperature. Okay. But is there, some hydrodynamics hidden in this data nevertheless? As we've discussed, the nature of the crossover from ballistic physics can be very delicate, and maybe there's something hidden in this data set. Okay, so then we used the largest width device, which is about 60 microns wide, and is believed to be 3 to 5 times larger than the actual impurity mean free path of this device. We used that channel to extract a temperature-dependent mean free path for impurity scattering. And then we could ask, is the temperature dependence of conductance in all of the narrow channels essentially explained by this bulk temperature dependence? So in other words, if we say, there's some ballistic contribution to the resistivity coming from the walls of the channel, and as well as a bulk contribution just coming from any rare impurity scattering that may happen in the channel, is the conductance essentially well captured? And it turns out that the conductance is very well captured if you normalize for its value at 0 temperature by a single fit parameter for all curves, basically parameterizing the roughness of the boundary together with the temperature dependence of the bulk resistivity that was measured. And so all the temperature dependence of this data is perfectly explained by ohmic behavior, and there's no viscous effects at all. So if we go back now and we ask, what was the Gaussian effect, or the hint of the Gaussian effect that was seen before, it's basically that these curves, the blue and purple curves, are not on top of each other. Okay? And the sort of strange mismatch and misordering of these curves as a function of width is basically the Gaussian effect that these authors, or the evidence for it that these authors have presented. But we think that in retrospect, this is some kind of experimental artifact. This system really seems much more compatible with just ordinary ohmic and ballistic transport. Okay, let me just skip my last few comments and just quickly summarize. So I think at least one reason to care about electron fluids is that it gives us a new framework for thinking about transport and dynamics in correlated systems. And it's one of the few tools that we really have, for very strongly correlated systems. It's worth really understanding as much as we can about it. At the same time, I'd like to emphasize that as we saw with palladium cobaltate, this hydrodynamic description is very sensitive to microscopic details, especially in an experiment where you're not deeply in a hydrodynamic regime. And I think this will be very important for interpreting experiments beyond graphene in near-term materials and devices. A sort of more forward-thinking question, but one that I could bring up, is what kind of imaging experiments, now that we've seen that we can image transport phenomena directly, what kinds of information do we have access to that were hidden previously, just in bulk resistivity? And then lastly, one sort of forward-thinking question is what other kinds of exotic hydrodynamics arise from quantum matter? I wrote a paper recently, for example, on constrained quantum dynamics and subdiffusion that arises in those systems. So, all right, with that, let me go ahead and take questions.
Okay, so if you have a question, please raise your hand electronically. Okay, Mr. Gochan.
First of all, it's Dr. Gochan to you. Onto the more actual question here. So, Professor Lucas, just one question that I had. You talked about how sensitive hydrodynamics is to the cleanliness, purity of your sample. Is it possible then to, because like most of the data that I saw on the slides here was like at temperatures in the hundreds of kelvins here. Could you, in theory, then conduct any of these transport measurements at a very low temperature, such that they are like effectively clean, that the collisions with impurities are more or less like snuffed out, or is that just not possible?
Well, the problem is that typically the impurity collision rate will stay finite at 0 temperature, and the electron scattering rate will diverge. So eventually you have to be at some intermediate temperature, and how low of a temperature that is really depends on the platform, on the material.
Got it.
Yeah, and in graphene it's usually hundreds of 100 Kelvin, but in gallium arsenide it could be 10 Kelvin. So
got it. Thank you.
Okay, and any other questions? So actually I had a quick question. So basically the hydrodynamic description basically requires some kind of like particle-like description, not necessarily like Landau quasi-particle, but you need some kind of quasi-particle. Now I know that some people have claimed that the strange metal phase, for example, is described by some like unparticle-like physics, where there is no really good particle description at all. So do you think the hydrodynamic description of the electron fluid would fail for these materials?
Okay, so firstly, I would disagree that even if you don't have quasi-particles, you can still talk about hydrodynamic phenomena. There's not really a ballistic regime in that case, but you can still think of a hydrodynamic limit as existing nonetheless. And so indeed, that's sort of part of the hope for the strange metal, is that even though we don't have a quasi-particle description, that at least, in certain regimes, we could kind of think of the hydrodynamic modes as the sort of quasi-particles in some sense. They are the slow degrees of freedom that exist in this system. So that was really that's the motivation for thinking about this in the context of strange metals. Whether that will turn out to be useful or not, I would say, is still open.
Okay.
I have one more question if no one else has one.
Sure, Dr. Gochan.
Mr. Lucas, so your paper with Caleb Cook for the hydrodynamics with polygonal Fermi surfaces, the data that you showed was with a hexagon. Like, did you, just out of curiosity, were other geometries for the Fermi surface considered, and did that heavily influence the conductivity data that you guys saw or results?
So we also considered a square. I mean, we just took polygons and
right.
Okay, you could also imagine a triangle, but that breaks inversion symmetry, and that's I think another beast that is interesting, but I haven't thought of so far. For a square, there's basically new kinds of hydrodynamic coefficients that come from essentially just the fact that you can write down more tensors with a lower symmetry. And if, for example, we look at if you look at, for example, this plot of conductance as a function of width, you can see that it's more sensitive to the angle. So even in the hydrodynamic regime, there's an angle dependence to viscosity that you could detect in principle.
Okay.
But yeah.
Thank you.
I have a question. So the hydrodynamics you are talking about here is okay for the Fermi liquid or non-Fermi liquid. Have you ever think about like topological insulator or even topological phases?
It's been on my mind. I haven't really done anything that serious about it, but I would say just more broadly, most of the focus on electron hydrodynamics has been on these isotropic systems, whether they're Fermi liquids or even graphene at the charge neutrality point, which isn't a Fermi liquid, but still is described by an isotropic fluid. I think there's a lot of very interesting things that could in principle arise in an anisotropic and especially in a topological Fermi liquid, but most of it is completely unexplored.
Okay, so maybe I have one more question. So I know you mentioned that you hope that you could apply this to the strange metal, but what about the pseudo gap?
I don't know that much about the pseudo gap regime, so I'm not sure I should say anything.
Okay. Okay, any other questions? Okay, so let's please all thank Professor Lucas again. Okay. So now let me stop recording.